Hello, everyone. Welcome to the sixth OpenCV webinar. Today, we are very happy to have here the CTO of OpenCV.AI, Anna Petrovicheva. Welcome, Anna. Anna is the CTO of OpenCV.AI, which is the for-profit arm of OpenCV. Besides devoting time to OpenCV, Anna also runs a startup which provides computer vision and deep learning solutions targeted at edge devices. As we've seen during the last decades, data is migrating first from on-premises to cloud data centers, and now from cloud to the edge. So is AI. Here, Anna is going to talk about AI on edge devices, its current status, as well as how to create an algorithm for a new problem. So, Anna, please.
Thank you for the introduction, and I'm happy to be here. Thank you for having me here. Let me share my screen. So yeah, my name is Anna Petrovicheva. I'm the CTO of OpenCV.AI. Let me first talk about a bit about myself to give you a more perspective into who I am. So I worked at companies like Intel. That was the main maintainer of OpenCV library, but in general, my career was tightly connected with OpenCV libraries. So I started developing computer vision solutions in 2010 and continue doing that up until now. So from 2010 to 2014, I was focused on classical computer vision algorithms, but then all the world, including myself, started switching into deep learning. So all the algorithms that I developed starting from 2014 are focused on deep learning and artificial intelligence. So at some point, I left Intel and started my own company that is called Inference.AI. That is focused on computer vision and deep learning solutions, and we mainly focus on the edge devices. And right now, I'm the CTO of OpenCV.AI. So let me first cover the current status of artificial intelligence solutions. So you probably all know that artificial intelligence changes our lives in very profound ways, and I'm sure that it will change our lives even more in the upcoming decade, right? So we already have some autonomous driving cars, but I'm sure that there will be more. I'm sure that artificial intelligence will help diagnose diseases more than it does now. It will help us play sports and entertain ourselves in different ways. And it will also help change the way the customer service and the way the shops work using artificial intelligence. So from my perspective, everybody knows that the artificial intelligence boom happened in 2012, right? So this is the point when everybody remembered that there is an algorithm called neural networks and started implementing it. So starting from 2012 to 2017, it was an exponential growth. So everything was growing so fast. The number of papers produced in artificial intelligence space and about computer vision and deep learning, number of smart people entering the field, right? So this is the case when many programmers, for example, who worked in adjacent fields started working on artificial intelligence solutions, which accelerated the industry so much. And also the amount of money that were invested into startups in this area was also growing exponentially up until 2017 or so. So starting from this point and up until now, this is kind of the new normal, right? So some call the artificial intelligence the new electricity, and I totally agree. This kind of became the new normal to implement artificial intelligence even into the business processes, even in the companies that were not connected with computer vision or deep learning before. So for example, in the oil industry, people start to implement artificial intelligence solutions. In agriculture, artificial intelligence is driving the progress. And in many other fields, we will see it growing in the upcoming decade, I'm sure. So let me talk about how to solve a problem using artificial intelligence. So I will mainly focus on images and videos here, but obviously the applications of artificial intelligence are not limited to these areas. It is also applied to other domains like texts and sound and time series. But I will talk about images and videos because this is the domain that I work with, that my whole career was focused around. So imagine that we have a new problem to solve, right? So this may be some problem that arises in our business. This may be a new job that we have to do, a new customer that we get. We need to solve some problem, and we wonder whether it can be solved using an artificial intelligence approach or not. So let's discuss several examples, right? So for the image on the left, imagine that we need to recognize the license plates. Now, in this case, every human, every person with a good vision system, with good vision, will be able to recognize the numbers on the car, right? So this means that if we have enough data, we will be able to train an artificial intelligence algorithm that does just the same, right? So we just need annotated data that is nice and visible and represents our target use case, and artificial intelligence will be able to solve this case. So for the image in the middle, I have no idea what is human-derived cells and how do they look. But human experts, people with biology, people who know biology or medicine, they know what it is and they can easily recognize them on this image. This means again that if we have sufficient data, we will be able to train an artificial intelligence algorithm that performs just the same as human expert does, like human who is easily able to recognize these human-derived cells on the image. Now, for the image on the right, imagine that we need to find all the people in the dark. But even a human with sufficient vision, even an expert, cannot be sure that, for example, I am not sure that I see all the people on this image on the right here. So this means that even if we have a lot of data like that, we won't be able to train an artificial intelligence algorithm that solves our problem because this data is ambiguous. We cannot easily understand what's going on here. And artificial intelligence doesn't do magic things. It just learns from data that is well annotated. So in this case, we won't be able to solve this problem with this type of imagery. But maybe we will be able to solve this problem using other types of imagery. For example, if we have thermal sensors that show the temperature of surroundings, we will be able to recognize people by their temperature because they are warmer than the surroundings. So we just need to be creative about what will be the type of our cameras, for example, here, and how do we approach this problem in some different way. So for so many algorithms right now, for so many problems are data-bound problems right now. This means the following. So when we have some problem, when we need to solve something, we may have two types of problems. One is algorithm bound, which means that it's very hard to create an algorithm that will solve our problem. And now another type of problem is a data-bound problem, which means that if we have enough data in our data set and it is well annotated, we will be able to solve the problem. So in recent years, artificial intelligence makes more and more problems, data-bound problems, which means that we just need to have the right data to be able to successfully solve our problem. So the process typically, when creating some industrial solutions for real customers, for real production use cases, the process of creating an artificial intelligence solutions looks like this. We collect the data. The more, the better. We need to annotate it in a very clear way. Then we take this data and train a model on top of that. And finally, we deploy it to the target environment, which may need some additional optimization to make sure that the model that we trained works in our target environment. So the general trend in the recent years is that artificial intelligence algorithms have been moving to the edge devices. So there are so many reasons for doing that. I will cover some of that, but first let me talk about what is an edge device. So generally, an edge device is something small and low power that works very close to the user, right? So this is not a server. This is not a big like personal computer generally. But in many cases, this is some device that is like very small, has very small form factor. So, for example, this may be a mobile phone. This is an easiest example of artificial intelligence device that can run a device that can run artificial intelligence algorithms and is very close to the edge. Another example of an edge device is some smart cameras, right? So smart cameras, they not only capture the imagery, but they also do some processing and analyze the data that they see, and may send to the server not the or the whole video feed, but some information that they detected. For example, I see two people, or I can understand like the number of the license plates of the cars that are visible, right? So smart cameras are another example of an edge device. So other edge devices may include sensors that, for example, are mounted on the ceiling and may not even have cameras on them, but some other devices like thermal devices, like thermal sensors. This may be some wearables, right? Some wearable devices. They also may have some chips that are able to compute some data, compute some algorithms on top of the data that they see. So this actually boils down to several chips, to several architectures that are used inside these devices. So one of the most popular architectures of like the platforms that are used inside these devices is ARM, right? ARM-based devices are everywhere, starting from the smartphones and all the way to wearable devices, to chips, to like smart watches, to smart cameras. ARM is very, very popular right now. Another popular choice is RISC-V architecture that is emerging right now. This is a new standard that is only like comes to our lives, but I'm sure that RISC-V will be growing in the upcoming years. We will see more and more applications for RISC-V devices. So RISC-V is slightly better than ARM in terms of the power efficiency, and also it's programmable. So we are able to customize it more for our needs. One other thing about RISC-V is that it's an open source standard, right? So it's completely transparent for everybody, for all the companies who use that, which is also a very good thing. So I'm sure that RISC-V devices will be used all over, starting from very small chips, very small devices, very energy efficient, and already some companies are developing servers that are based on RISC-V technology. So another choice for edge devices is FPGA, programmable chips, right? That are built around specific algorithms. One downside of FPGA is that they are hard to work with. You need to write specific code on VHDL language to make it optimized. But a good side of it is that your FPGA is specifically created for your algorithm, which makes it very, very efficient for your specific algorithm. Now, there are solutions from several popular companies, and probably the most popular solution right now is NVIDIA Jetson. So Jetson runs on ARM, but also has an NVIDIA-specific compute core that is able to that has GPU, right, and is able to run neural networks in very efficient way. So another choice is Google Coral, which is a device from Google, obviously, which is specifically created for TensorFlow library, right? So it's very efficient in matrix multiplication, and thus it's very fast in computing neural networks. So Intel Movidius is one more choice. It's based on myriad processors that are again created specifically for neural network inference. And also CPU may be considered an edge platform because in some cases, these like smart cameras, smart devices may just run on like CPU from ARM, or sorry, from AMD or from Intel. And you can also like optimize neural network for inference on CPU from Intel or from AMD. So the good thing about these platforms is that typically edge devices are very low power. For like specifically, this goes about FPGA and RISC-V devices that can run on the same battery power without connection to power cord for up to 2 years on the same battery power. Which is fantastic, right? So these chips that can run artificial intelligence algorithms, you don't need to change a battery for 2 years on them. So let me talk about the reasons of why moving to the edge devices makes so much sense, right? So the general approach was to run the artificial intelligence algorithms on the servers, which would make the pipeline the following. So imagine that you have a camera that wants to track people to understand how many people are in the store, in the shop, right? You would need to send all the videos that this camera sees to the server, to, for example, some cloud or some like server, in-house server, that would process this data and send the results back to the camera, for example, or show them in some web interface. This would mean that you would need to send a lot of internet traffic, right? So these videos would be pretty heavy and you would need to send them in real time, which means that your speed of the solution would not only be limited by the speed with which the server works, but it would be also limited with the speed of the internet traffic. The other point about that is that so it would be like you would need to organize this solution in some stable way to make sure that this solution is very stable because it needs to be connected to the internet all the time. So when you move the artificial solution to the edge devices, for example, you have smart camera that can compute the number of people right on the edge device close to the camera, but it would mean that it would only send a very small number of information to the server and to the web interface, right? So it would analyze the number of people right on the camera and would just send the number of people to the edge device, which is a way more optimal way to solve this problem. The other reason is server costs, right? So you would need to pay for the cloud, you would need to pay for the server, and these costs are actually pretty high. So by moving these solutions to the edge device, you basically pay for the power and you pay for the device. But in general, these costs are much less than paying for the server. And the final reason is security and privacy. In many cases, in many countries, you cannot provide a solution that sends all the information to the cloud and can store it there. Also, there are some sensitive cases, for example, in medical information, you cannot just send all the information to the cloud because it can be hacked, it can be stolen, the information can leak, right? When you process all the data on the edge device, there is no question about security and privacy because you only send a very small amount of anonymized information to the cloud, which makes it way better and way more secure approach to solve artificial intelligence problems. So let me talk a bit about edge device optimized inference, right? So I talked about why moving to the edge devices makes so much sense. But it also comes at the cost of optimizing the neural networks for edge device optimized inference. First, artificial intelligence models are very heavy. They are big, they can be up to 1 gigabyte in size. They require a lot of memory to be inferred, and they actually require a lot of computations, right? So state-of-the-art models, they required hundreds of teraflops to run single inference on the single frame. But if you want to run the solution on edge device, you would need to very, very much optimize this artificial intelligence model to make sure that it can run close to real time or real time on your edge device. So this optimization is not easy. You would need to optimize it on several ways. And the first way is algorithmic optimization. So you would just need to come up with a more optimal approach to solving the problem, maybe a smaller artificial intelligence model. To read some state-of-the-art papers about very small models is a good starting point for that. So as an example, in one project that I worked on, we were able to compress a people detection model for FPGA to 600 kilobytes using algorithmic approaches only, right? Without using low-level optimization, programming in like specific languages. We didn't use any of that. We just optimized the model that we were working with, and we were able to compress it to 600 kilobytes instead of 50 megabytes that we started with. So another thing that helps you to optimize the model is that the artificial intelligence models are highly redundant. They include so much computations and so much information that are not actually needed for the target task. So when optimizing such model, it would be great to get rid of the computations that are not needed for your target use case, for your target model. From our experience, you typically can compress a model using quantization or pruning. So you could compress a model 2 times or even more without losing an accuracy, because you see this plot on the left, it's not linear, right? So when you compress a model, when your model becomes smaller and smaller and smaller, you cut out some part of that. The quality doesn't go down linearly, it goes down with a curve, which means that you could cut out a pretty big part of the model, get rid of it, without sacrificing a lot of accuracy. And just by that, in this specific example that I was talking about, using these techniques like quantization and pruning, we were able to compress the model from 50 megabytes to 600 kilobytes. So once again, if you want to compress a model for an edge device, for edge inference, several things that you would need to do is first to use a smaller model as baseline, read papers about the state-of-the-art small models to start with. Then when you trained your model, you would need to quantize it and run a pruning algorithm. So quantization and pruning are neural network compression techniques that are very popular right now. There are open source solutions for that. And I totally recommend using them if you want to port your model to the edge device. So when you port your model to the edge device, you would also need to use specific tools. And these tools would heavily depend on the type of the device that you work with. So these tools, they form a very scattered market. So for training neural networks, like several years ago, maybe 4 years ago, there were so many different frameworks for that, right? So first there was Caffe, then there was Caffe 2. There were some strange frameworks like Darknet or Lasagna or Chainer or MXNet. There were so many different frameworks to do that. But right now, in terms of training, there are 2 major leaders for neural network training, which are PyTorch and TensorFlow, right? So pretty much everyone trains neural networks either in PyTorch or in TensorFlow. But for inference, people still use so many different frameworks that include TensorRT, TF-Lite, OpenVINO, CoreML, PyTorch, and even OpenCV has a framework for deep neural network inference that is based on OpenVINO. So the reason for that is that these frameworks, like every framework, is basically optimized for a specific type of device, right? So if you want to run your solution on NVIDIA Jetson, your choice would be TensorRT. If you want to run on an Android phone, your basic choice would be TF-Lite. If you want to run on iOS device, your choice would be Caramel. So for example, if you're working on an application for mobile phones, you would need two different frameworks and two different, like to convert to two different frameworks to have optimal inference for Android and for iOS. If you are targeting Intel CPU or VPU like my videos, your top choice would be OpenVINO or OpenCV.AI module that is based on OpenVINO. And finally, there is an emerging PyTorch mobile framework that would also be very optimal for devices, but it's not a leader yet. Even further, so if you focus on frameworks, if you focus on hardware like RISC-V, you would need some custom inference framework that is typically provided by the developer of the platform. If you work for FPGA, you would need to implement your inference on VHDL, like low level, and so on. So if we speak about the inference of neural networks, this is still a very scattered market. You would need to know and to implement your neural network in different types of frameworks and even languages to make it very optimal on each device. So let me summarize what we were talking about today. So first, we discussed the current state of artificial intelligence and how it changes our lives in profound ways. Then we covered what is a data-bound problem and how to understand that your problem, the problem that you have, can be solved by artificial intelligence or not. We also covered what the pipeline of creating an artificial solutions for the edge looks like. We discussed why artificial intelligence is moving to the edge and why it is a very smart move. And finally, we discussed how to move your artificial solution from server to the edge device. So I will be very happy to answer your questions. Thank you.
Okay, thank you, Anna. That was a comprehensive talk. So let's see if we've got some questions from the audience. If you have any questions, just write down in the chat section. English, Chinese, both are okay. So here are some questions. You talked about compressing a people detection model from 50 megabytes to only 600 kilobytes. That's impressive. So, but besides the model size, what else should we consider when we do some optimizations on edge devices?
Sure. So thank you for the question. This is a very good question. So first, like apart from the size of the model, we should also focus on memory consumption because typically the size of RAM, the size of the operating memory is limited on the edge devices. Then we would need to understand the energy consumption of the model because if your model runs on battery power, if your device runs on battery power, this is also very important. And finally, like it depends on the priorities, but you obviously need to care about the runtime, about the speed of the inference of your model. So basically, this boils down to the number of operations, the number of computations you have. So this is measured in like teraflops or megaflops. This is something that you need to care about also.
Okay. So do you work with different platforms? Like when you train a model, so you train a model in just maybe in just one or two format, but you have to port to different platforms. So how do you do that?
Yeah, exactly. So my preferred framework for training is PyTorch. I always train neural networks in PyTorch. But then if we need to, like when we need to port the network to the target device, we use specific frameworks to port it. So for example, if our target hardware is like mobile phones, like Apple iPhones, right? We would need to convert this model into Caramel. to run it in a very efficient way on a phone. So there are several ways to convert a model. Typically, like in some cases, for example, in CoreML, the Apple provides frameworks to convert your model from PyTorch to CoreML. In some cases, you would need to manually convert that. So, for example, if converting a model to TF-Lite, there are tools that you can use to automatically convert your model. But from my experience, it makes more sense to do it manually to avoid data conversion, because there is like PyTorch and TF-Lite, they use different format of data storage. And to make the inference more optimal, it would make sense to just convert the data, the model manually to TF-Lite and have the more optimal way to infer your model on Android device.
Okay. Since computing is moving from cloud to edge, so can you give us an outline about what OpenCV is doing to better support edge devices?
So one of the major initiatives that OpenCV had the last year is, so OpenCV has a DNN module that is able to infer the neural networks in a very optimal way. So a big part of this DNN module was optimized for very, very different types of devices. And one of the recent additions to OpenCV library that we are very happy about is thanks to a company, a Chinese company that is named OpenCV.AI Labs that contributed a framework that is called T-Engine that accelerates the inference for ARM devices. So this is a major thing in OpenCV, very recent, that we are very happy about. It helps move the computations from the server to the edge devices.
Okay. So are OpenCV going to support NPU?
Yes, but we don't have a close plans for the next release in doing that. So in future we will definitely support NPU, but not right now.
Okay, so next release is OpenCV 5.0, right?
Yeah.
So
yeah.
I think it will be released probably early next year, right?
Yeah, so we target for early next year, and we have so much plans for OpenCV 5.0. Yeah.
Okay, so then what should we be expecting for OpenCV 5.0, like some new cool features, new modules, etc.?
Sure. So to give you a sneak peek into what OpenCV 5.0 will look like, one of the things that will be a major addition is 3D module. So we will have a module that is specifically focused on 3D algorithms that we expect will be very popular among the community, because 3D data becomes the new normal. So more and more devices are able to capture data in 3D instead of 2D. For example, the recent iPhones and iPads are able to do that. So because of that, we are adding 3D module, 3D functionality. And again, a part of that is due to our development partnership with a company, Chinese company that is named Orbeck, that produces 3D cameras. And we will work with them, we already work with them on 3D algorithms and support for 3D data processing. Just to give you a sneak peek into what OpenCV 5.0 will look like. So we are moving the Python releases. So previously OpenCV Python releases were released by the community. But right now we are moving the releases to our core team to ensure better compatibility with systems like Ubuntu, to make sure that, for example, Windows system, ImShow functionality always works in systems like Ubuntu. And in general, the solution is better tested. We are moving the releases to our core team. So one more thing that we expect to see in 5.0 is many algorithms from the recent Google Summer of Code that include different algorithmic improvements, as well as speed ups to the library. support for new platforms. So, for example, we have initial support for RISC-V platforms there, bindings for new languages like Julia bindings, and many other features like that.
Oh, cool. So I think the Python release is really cool and useful. Okay, let's see if
Thanks.
we've got other questions from the audience. Mm, okay, seems that there's no more questions. Okay, so if there's no more questions, I think that will be all for today. Uh,
Thank
thank
you
you,
so
Anna,
much.
to our webinar. Okay,
Thank
and
you.
thanks for watching and see you at the next webinar. Bye bye.
Bye.